So, we have an integral to do. Integral from minus infinity to infinity, log of x squared plus 1 all over x squared plus 1 dx, which cannot be done by the usual methods of high school integration. So, what is the clue to this one? Well, let me observe that if x is real, then x squared plus 1 is equal to x minus I by x plus I, and the log of that, which is equal to the log with capital L of that, is actually equal to log of x minus I plus log of x plus I. Now, how do we know that this is true? Well, a capital L log has got a real part and an imaginary part, and the real part is just the natural log of the modulus of this, and there's no problem with that. The imaginary parts are to do with the argument of this, the argument of this, and the argument of this. But notice that if I've got a number x, then x plus I is here, x minus I is here, and say if here is 0, then the argument of x plus I and the argument of x minus I, well, one is the negative of the other. This is obviously a symmetrical situation, and so the argument of this is negative the argument of this is negative the argument of this, and the arg parts of the logs cancel out. So that means that we can write it as integral minus infinity to infinity log of x minus I over x squared plus 1 dx plus integral minus infinity to infinity log of x plus I over x squared plus 1 dx. Now, the first of these can be done by noticing, first of all, that in the let's do this one first. Let's do this one first. If I replace x by z, when z is in the upper half plane, then z plus I is strictly in the upper half plane, and it stays away from where log is not continuous or differentiable or whatever. So log of z plus I over z squared plus 1 is analytic in the upper half plane and has a singularity except for the singularity at I. So this is analytic in upper half plane except at I. So in the upper half plane, I'm allowed to take one of my standard contours like this, and if I do an integral around this contour, I will get that the integral around this contour is equal to 2 pi I times the residue of this function at I, which you can calculate without too much trouble at all. And then one shows that the integral around this part goes to 0 as r goes to infinity, and as r goes to infinity, this integral tends to, well, what does it tend to? It tends to this integral. And so in the end, this integral is equal to 2 pi I times the residue, and that enables us to calculate this one. Now, For the other integral, we have to argue slightly differently. We have to do a contour in the lower half plane. And we have to take a singularity at minus I. And the reason is that log of z minus I over z squared plus 1 is analytic in the lower half plane and on the axis, but there is this singularity here. But we can do more or less exactly the same argument to take care of that, and that takes care of this problem.